Good afternoon. I'm a second-year PhD student in Professor Song Han's lab in University of California, Santa Barbara. Today I'm going to talk about our recent publication in JPCL, Truncated Cross Effect Dynamic Nuclear Polarization, and Overhauser Effect Doppelganger. Just like Ned from Simpson and Walter from Breaking Bad, we observed a DNP mechanism mimics all the features of Overhauser effect, but it's actually a truncated cross effect. I'll explain in my talk how we solve this puzzle. So first, I'll explain why we want to use DNP. As you may know, NMR is basically detecting the population difference between the two nuclear energy states, and this is called polarization. Polarization is calculated as this formula. There are three solutions to increase polarization. First is to increase magnetic field B0, second is to decrease temperature T, and the third one is to induce hyperpolarization method. Dynamic nuclear polarization, or DNP, is the most commonly used hyperpolarization method. Then what is DNP? DNP is basically transfer polarization from electron to the hyperfine coupled nuclei through certain microwave irradiation. And theoretically, we can achieve 660 proton DNP enhancement. Here's one example of using DNP on tau fragment. Sample is provided by Professor P.K. Madhu from T alpha. And with DNP, we are able to achieve 150 enhancement. This means that if we detect the blue spectrum with 1 minute, to have the similar signal-to-noise ratio, we need 16 days for solid-state NMR.
Then how DNP experiment has been done? I used the commercial Bruker DNP NMR setup to explain. Gyrotron here is the high-power microwave source. Microwave is guided through the transmission line to the MAS probe inside the NMR spectrometer. Inside the MAS probe, there's our sample rotor, and inside the rotor, we have stable radicals that can provide free stable electrons. Also, we have our target sampling. Glassing agent is also needed to provide cryoprotection to target sample, also for spin diffusion purpose. One of the most commonly used glassing agent is DNP juice, which is a mixture of deuterated glycerol, D2O, and water. During DNP experiment, microwave first irradiate at free electrons, and then the polarization will transfer from electron to the nearby hyperfine coupled nuclei, for example proton. And then through proton network, polarization will diffuse to our sample. A lot of effort has been devoted to improve DNP enhancement under high field conditions. Broadly speaking, there are three pathways: instrumentation development, improving sample preparation method, and improving DNP theory. My talk today is covering all the three aspects. So first, I'll talk about the instrumentation in our lab. All the experiments shown in this paper are done using our home-built DNP setup. So we are using a 300 MHz Bruker NMR spectrometer. Inside the spectrometer, we have a cryostat, which can be cooled down to 3 Kelvin using our liquid helium cooling system. And here's the microwave part. Microwave is generated from the microwave source and goes through the quasi-optics component. Then microwave is guided through the corrugated waveguide and reach the NMR probe, where our sample is located in. Also, with this pulse-forming unit, we are able to generate arbitrary waveform pulses, and with this whole setup, we can also do high-field EPR detection. So this setup allows us to have a deep look into the DNP mechanisms at different conditions, which is very critical in improving DNP enhancement. Broadly speaking, there are three DNP mechanisms: Overhauser effect, solid effect, and cross effect. Both Overhauser effect and solid effect are two spin systems, which involves one electron, one nuclear hyperfine coupled. For Overhauser effect, microwave irradiate at on-resonance condition, which is a loud transition and requires less microwave power. And En cross relaxation is necessary for Overhauser effect. In cross effect, microwave irradiate at off-resonance condition, which is forbidden transition and requires more microwave power. For a cross effect, it's a three-spin system, which requires two electrons coupled, and they are unequally coupled to a nuclei. And the matching condition for cross effect is the two electron Larmor frequency difference equals to the Larmor frequency of the coupled nuclei. In cross effect, microwave irradiate at on-resonance condition, which is an allowed transition and requires less microwave power, just like an Overhauser effect. Then how do we distinguish DNP mechanisms? One of the standard experiments to distinguish DNP mechanism is frequency profile or field profile, which is basically DNP enhancement as a function of microwave irradiation frequency or field. Here's an example of BDPA field profile observed in Professor Griffin's lab in MIT. They assigned the enhancement coming at BDPA center frequency as Overhauser effect. So how do they assign it? I'll use this energy diagram to explain. When one electron, one nuclear hyperfine coupled, the energy states will split into four, and the ball size here indicate the population at different energy states. So for Overhauser effect, microwave irradiate at on-resonance condition, which is single quantum transition, and will saturate the electron energy states. If the cross-relaxation rates are different, it will reach a new quasi-equilibrium state where the polarization increased. And that's why the enhancement coming at the BDPA center frequency is assigned as Overhauser effect. And for the two enhancements coming at omega naught h apart from the BDPA center frequency, they assigned this two as solid effect. Then again, how do they assign it? I use the same energy diagram to explain. So for a solid effect, microwave irradiate at forbidden transition, for example, double quantum transition, and will saturate these two energy states. And then the nuclear polarization will increase. Similarly, if microwave irradiate at the zero quantum transition, these two energy states will be saturated and the polarization increased. Another experiment to distinguish DNP mechanism is through power sweep, which is DNP enhancement as a function of microwave irradiation power. So here, they picked the optimum field for Overhauser effect and cross effect, then sweep the microwave power from 0 to 12 volts. They observed that Overhauser effect saturate at low power, while solid effect saturate at high power. If you still remember, I mentioned that Overhauser effect requires microwave irradiate at on-resonance condition and need less power to saturate, while solid effect microwave irradiation is at forbidden transition and requires high microwave power. So again, this verify what they speculate as Overhauser effect and solid effect. However, this Overhauser effect plus solid effect observation is very surprising, because conventionally, Overhauser effect is only known to exist in liquid state or in conducting solid, not in insulating solid. Because Overhauser effect requires En cross relaxation or a fluctuating hyperfine coupling, which is normally not known in insulating solid. One of the explanations of Overhauser effect in BDPA is that because BDPA has this special conjugation structure, and this can act as a source of fluctuating hyperfine coupling. What actually surprised us is that we observe a similar solid effect plus Overhauser effect in the TCP trital mixture in DNP juice, which is completely different from the BDPA case. TCP is a broadline nitroxide radical provided by our collaborator, Professor Andrew Reika from University of Nebraska-Lincoln, and trital is a narrowline radical. So here's the frequency profile for TCP trital mixture in DNP juice at 4 Kelvin. The enhancement at trital center frequency, we assign it as Overhauser effect, and I'll address it as OE star for now. And the two enhancement, which is omega naught H apart from trital center frequency, we assign them as solid effect. Then we picked the optimum frequency condition for OE star, then sweep the power from 0 to 120 milliwatts. Then we picked the optimum condition for solid effect, also sweep the microwave power. From here we conclude that only with around 7 milliwatts microwave power irradiation, we are able to achieve the maximum OE star enhancement. But with 120 milliwatts, we're not able to saturate solid effect at all. And we observed a similar frequency profile across a large range of temperature from 3.3 to 85 Kelvin. Then we are wondering where the Overhauser effect enhancement comes from. Does it from trital itself, or is from the TCP trital mixture? So we changed the radical composition and obtained different frequency profiles. Without adding any TCP, trital itself only shows solid effect. There's no Overhauser effect enhancement coming at the trital center frequency. When we add 5 millimolar TCP in, OE star enhancement starts showing up. When we add more TCP into trital, the enhancement first increases and then it reaches the plateau. Why would I say initially our observation of OE enhancement in TCP trital mixture is very surprising? Because unlike BDPA, neither trital nor TCP has the special conjugation structure. It means that there's no fluctuation in hyperfine coupling, which can induce EN cross relaxation rate. So it seems that what we observe is contradictory to the existing theory. So the question arises, what DNP mechanism we actually observed? To solve this puzzle, we used our high field pulse EPR setup to measure the electron spin dynamics. First, we measured T1E at trital center frequency of 15 millimolar of trital in DNP juice at 4 Kelvin. And we measured a T1E of 15 milliseconds of trital. When we add 5 millimolar of TCP, T1E of trital decreases significantly. And then when we further increase the TCP doping amount, the relaxation rate didn't change that much. So from here, we conclude that TCP and trital, they are interacting. However, when we measure T1E at trital center frequency, we are not able to observe any echo coming from TCP. We also conducted electron double resonance or ELDOR experiment to the system. ELDOR is basically a pump probe experiment where we saturate electrons at pump frequency and then use solid echo to detect how saturation transfer to the electrons at probe frequency. In our case, we set the probe frequency at the trital center frequency and then sweep the pump frequency across the TCP frequency range. Here's the ELDOR spectrum for 15 millimolar of trital. The hole around trital center frequency indicate the spectral diffusion. When we add 30 millimolar TCP into the system, the hole around trital center frequency become much narrower, indicate that the spectral diffusion of trital become much less when TCP is doped. Also, I didn't show here, but when we set the probe frequency to the TCP, we are not able to saturate TCP at all at any frequencies. So from the Eldor and T1E measurements, we conclude that trital and TCP, they are for sure interacting. However, there's no spin echo observed from TCP, which indicates that spin relaxation rates of TCP, they are too short to be detected. To verify our hypothesis, we did numerical simulation. So we set TCP as a fast relaxing agent, and trital is a slow relaxing agent, and TCP trital, they are dipolar coupled. So in here, x-axis is the microwave irradiation frequency, y-axis is the normalized echo intensity. For trital, we are able to saturate trital around the trital center frequency. However, in TCP, we are not able to saturate TCP at all, similar to our hypothesis. And then we took this system and cut out the Hamiltonian for EN cross relaxation to make sure that Overhauser effect doesn't exist in this case. And then we are able to simulate this frequency profile very similar to what we observed experimentally. We observed there's an enhancement coming at the trital center frequency and the two enhancement for solid effect. So from here we conclude that fast relaxation of one of the two electrons truncate the cross effect DNP, and it mimics the features of Overhauser effect. Another interesting observation is that TCP itself cannot dissolve in DNP juice. Only with the addition of trital, TCP can be dissolved. So we think that maybe TCP is clustered inside the system. That's why TCP relaxation rate is so fast, and trital is assisting for the cluster to dissolve in this case. Then we did X-band EPR measurements for TCP trital mixer in DNP juice and in DMSO. So in DNP juice, TCP is clustered, but in DMSO, it is not clustered, just like what we speculated. Then we picked the two conditions and obtained the frequency profiles of the two. In DNP juice, TCP trital mixer again shows the truncated cross effect plus solid effect frequency profiles. But for DMSO, the apparent DNP mechanism become cross effect. This is interesting because just by changing the solvent, we are able to tune the apparent DNP mechanism. Also, this again verified that TCP trital mixer in DNP juice is not Overhauser effect plus solid effect, but actually truncated cross effect plus solid effect. So our conclusion here is truncation of cross effect is observed if one of the two participating electrons has very fast relaxation rates, and the truncated cross effect mimics Overhauser effect features. So finally, I would like to thank for Professor Song-Yi Han for all the guidance and giving all the opportunities. Also, Professor Andrew Raika for providing new TCP radicals, Dr. Asif Iqbal for all the help in experiments and numerical simulations, Dr. Ilya Kamenka, Dr. Alyssa Livesley for setting up the instrumentation, also for help during experiments. Thanks for Dr. Shidao Jane for all the valuable discussions and advices. Thanks for our group for providing such a great atmosphere for research. Also, I'd like to thank for IRIS program, NIH, and NSF for funding. Thank you for coming here listening to my talk. and showing me around in Raybon University. Thank you.